Hey guys. Oh, I would actually. Is it the Girl Scout cookie season?
Yeah. I'll just leave downstairs. I'll just.
Oh, really?
Take a picture.
Oh, let's take one. Thank you though.
Yesterday used not that price for like 45 years.
Vibrations. I'm pretty sure like. When he was talking, he always teaches the. What's this exam?
Oh, yeah, yeah, he's gonna be in the summer, which is good. It's good for him. I'm taking a little something.
It's so funny. I keep leaving this on here. It's just every single time I do a tab, it's just on there. It's scary.
Trying to desensitize yourself.
I guess so. I don't know. I just keep getting back to the tab. Okay, Trent, you know that's the monkey from Toy Story 3?
Mhm.
This guy.
Oh, yeah.
It haunts my dreams. You
Oh.
know?
I'm sure you're not alone in that.
That's just a fun fact. I have to tell people.
Oh my gosh.
And now every single time I just think of it.
Well, hopefully he'll leave. Leave your thoughts after a few weeks or so.
But Finland's why not? Do they like
I like the Samoas.
really? I don't like that like the Samoas and like the Cylons, they always come in like a different like not like that.
Oh,
you know
yeah.
what I mean? Like so you get less of it and it's still $6.
True.
Honestly, the day that they changed it from $5 to $6 is the worst day of my life. Because I had a 20 today, right?
Sounds like you've had a pretty good life.
And I had a 20, right? And then that means I can only buy 3 boxes and not
3 boxes and stuff. Well, yeah, that's true, actually.
that's so terrible.
Man, inflation even the Girl Scouts, huh? Even the nonprofits have to raise their prices.
Same. Name community.
Yeah, that's the problem. You can get a whole box in one sitting. You could do that on purpose. Do that. Chick I was talking about this morning. The woman who got like open UCI.
Oh, really?
Yeah.
Yeah, I should have.
Wait, I didn't tell you this story about the TikTok. She's in her last semester of her master's program. And she might not have all her clinical hours. So that means she's gonna have to do one more semester, possibly. If she can't get another. No, she's not going to UCI. UCI is the hospital she's interning at. She goes to Iowa.
Oh.
So she might have to do a whole other semester of Biola, which is worse than UCI. Like Biola's like Biola's like 30 grand a semester.
30?
It's a private Christian school. Trump is expensive. Dr. Tran, be careful what you post on TikTok and Instagram. You could get fired.
Oh, I'm aware.
It's crazy. My friend just got let go. Well, yeah, she's my friend. She got let go from UCI for posting a TikTok.
Oh, really?
Yeah, because her badge was showing and stuff.
Oh, my gosh.
She was interning there for SLP and now she might have to retake a whole other semester of her master's program.
Oh,
This is her
gosh.
last semester too.
Oh, man.
So
Oh.
she gotta be careful, man.
Yeah.
Digital footprint.
Yeah. Nowadays, anything you put online is there.
Yeah, you just. Yeah.
It's quiet. It's next to me.
Uh-oh.
I can record you.
Oh, no.
I remember that.
She'll remember that.
It's okay.
No, this isn't okay.
No, it's okay. She can do whatever she wants because she bought me Taylor Swift tickets.
Damn. Mo, did you dress up in pink,
I
bedazzled?
did.
Yes, but it's the only way to do it, right?
Hey, that's what happened.
That's
That's
all.
all the fucking video was.
I gotta make a video right now.
You're gonna get 5 minutes.
Dr. Tran's gonna find my video when I'm in Dr. Tran's class and I want to kill myself.
That was the trend, and that's how she got.
Oh, really? Oh,
Yeah,
my gosh.
literally.
Oh, man.
This is like even then, it's like
Every day I'm.
it's like after week
No, dude, I
one,
just watch shows on that Kians.
like homework one.
I
So
know.
that's how I feel now. It's like it's already one minute.
The other day I was running Kians and I was watching a show and stuff like, why are you watching a show? I'm like, "Cause this is boring."
What do you say?
You just looked at me and went, okay, just walked away. We aren't supposed to do that.
It's like, there.
Dude, no, I have had it before where like Cosell walks in and I'm watching something and they don't say anything to me, dude.
We're pretty.
It's true. Dude, and Hyman is so silent now.
I do.
Yeah, the dude who's in shipping.
The tall one.
Yeah, he's the one that strengthens here sometimes.
Oh, it's the one that.
Oh, yeah, he made his life mistakes. All he does is talk.
Like, it's fairly succinct.
Yeah.
Much of them were his.
I don't know. I mean, it was the shipping as well.
Make sure that people who want to tell me, and I really have to do what they have. Oh, I like.
Are we gonna do like polar coordinates and stuff in this?
Oh, yeah. We're doing, well, we're only just doing 1D, but we're gonna do spherical stuff today.
Are you gonna make it really simple for us?
It's not gonna be terrible, in my opinion. but-
That's.
You
the
did go to
thing.
Stanford though, so.
Your lectures, like, it makes perfect sense, and then you like, look at the homework, it was, whoa,
That's what he's trying to do. He's just trying to make us see him in office hours.
That's the option.
I am kind of lonely in office hours. I do like it when you guys come.
That's-
Yeah. Keep it like separate. Do you think the fundamentals of engineering, do you think that exam and like certificate is really valuable?
I don't know. I've heard different things. I actually don't know that many people who've gotten it among my friends that are engineers.
Yeah.
But the ones that do have it say that it is really valuable. I think it depends on what company you end up working for. Because my uncle actually, all the time, he always tells me to get it because he's made his career at Caltrans.
Yeah.
And Caltrans, they really value that. Yeah. So,
Oh, California, right? More like transition bridges and stuff.
yeah. Yeah. So he always tells me to get it, but then,
That's civil.
yeah.
Civil engineers, they have to get it.
Is he a project manager?
Yeah, he is.
That's probably why he passed.
Yeah.
See, that's what I don't understand. I was thinking about this the other day, like, if you're a project manager or a CEO of an engineering company, you should know engineering, like
course.
the CEO of Boeing, he got his degree in accounting.
Yeah, no,
He's
it's,
the new one. Yeah, the new one. He got his degree in accounting.
That's why.
It's
I mean,
so
that's
ridiculous.
kind of the source of a lot of their problems is,
It's because they keep on hiring dudes who don't know anything about engineering.
yeah, all the business MBA people.
Yeah.
I think it's.
No, I think I know what I'm talking about. I won't fall, dude. My knees locked in underneath the table. You think you could like? Have you ever done the escape room and stuff?
I think we.
We did an escape room the other day. We did this, me and Cora, we did like some escape room and we like went and we solved this like complicated escape room in probably like 6 minutes. It was really fast. It was in Corona.
Oh, okay. Yeah, that's the science. You guys doing?
Saturday.
Oh, Sunday. You're all day.
I should. I have to meet, we're meeting with our mentors in the early afternoon, so I need to fix it. It's like over my head, dude. I think about all.
Okay.
And then I go and look at it, I'm like, oh, dude, I know what I have to do.
Work on it. It's like Friday morning before work and then Saturday morning.
Yeah,
That should be enough.
I need to take my desktop to my show center.
It's all over there.
It turns on, but it doesn't display on my monitor.
So VGA or display board? How are
Yeah,
you?
like HDMI straight into the graphics.
You try to do.
I did. And then I also tried like unplugging my RAM, back in, unplug my, I did that whole thing, right? Unplug it, I cleaned it, and I unplugged it.
Have you tried it like on a new monitor?
That monitor works. Like I plug in my other computer. I wish I had a better laptop, like that. I don't talk to you.
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. It's wet, rainy outside. Hopefully everyone's staying dry. Okay, so today, today the homework's due, so remember to get that in, on Canvas, or if you have it in person. No one's turned in anything in person in years, but I'd be very happy to accept it if you want to turn in person. Okay, so plan for today is we're going to continue on with radial systems. So last time we were here, we did a couple heat equation type problems in cylindrical coordinates. We did one kind of simple example and then one example with a solid cylinder. Today I'm going to show you guys how to do thermal circuits in cylindrical systems. And this is going to bring up a really interesting concept called critical thickness, which we'll discuss in a bit. And then I'm hoping second half of the class today we'll move on to spherical systems. So we'll solve heat equation in spherical systems. And then hopefully wrap this up, maybe not today, but maybe on Tuesday. All right. Any questions I can answer before we get started? Okay. All right. So let's go ahead and get started. Okay. So first thing we're going to cover is thermal circuits in cylindrical systems. Okay. So this concept of thermal circuits that we kind of first introduced in planar systems can also be used in cylindrical systems, right? And in fact, last time we didn't really do anything with it last lecture, but we did derive the equation for a thermal resistance in a cylinder. Or I should say the conduction resistance. Okay. And so the situation that we were looking at for this was something like so. So if we look at kind of a cross section of a cylindrical system, so I'll kind of just, I won't draw the whole cylinder here, but I'll just draw kind of a slice. Okay. And so for a certain cylindrical system, if we had basically two, an inner radius and an outer radius, we have an inner temperature of Ti, outer temperature of To. The radius at this inner part is Ri, and the radius at this outer portion is Ro, okay? So what we said last time is that we can compute, so let's say that Ti is greater than To, right? So our inner surface here is hotter than the outer surface. And so what that's going to do is that it's going to drive heat transfer out that way, okay? So the equation that we derived last time was that the heat transfer from the inner layer to the outer layer was equal to Ti minus To divided by the thermal resistance of that cylindrical layer. And so that that resistance was natural logarithm of Ro divided by Ri divided by 2 pi K thermal conductivity times the length of the cylinder. All right, and of course, the length of the cylinder, you can't really see it in this picture, but the length of the cylinder is just the length in the direction going into the page. Okay. So this quantity right here, this quantity right here is the conduction resistance of a cylinder of a cylinder. Okay. Okay. Now, of course, you know, this caveat here is assuming that the temperature is going from the inner part of the cylinder to the outer part, right? So that part's really important. So, you know, I'm going to kind of addend this to say this is the conduction resistance of a cylinder in the radial direction. Because there's a difference whether you have conduction, you know, going from the inner part of a cylinder to the outer part, or if you have heat transfer going down the barrel of the cylinder, right? So you have two different situations. But this one right here is specifically just in the radial direction. Okay. So heat transfer going from the inside of a cylinder to the outside, or from outside to inside. It works for either direction, but or either radial direction, but not going down the axial. Okay. Okay, so let's see what this looks like in an example. So just like in the planar case, you know, thermal resistance. Oh, question, yes.
Does that inequality of the temperatures have to be true for that equation to be true?
Not necessarily. So if it's the other way around, and so if it's To, if To is greater than Ti, the only thing that would change is that you would change the order of these two right here.
Okay.
Yeah. So you just want to make sure that the temperature difference is always positive. So you do hot temperature minus cold temperature, but the conduction resistance itself doesn't change.
What about the natural log? RO be under in the denominator and the RI would be on top.
So that one's always the same. So that one you want RO over RI, because if the smaller radius was on top, then the resistance would be negative. Yeah. Question.
But it is possible to have a negative for Q. Is that true or no?
So a negative Q just means that the heat transfer is going in the opposite direction.
Oh.
Yeah. Yeah. So if you do actually, there are situations where, you know, maybe you don't know ahead of time which surface is hot or cold. And so you just form the equation like this, and you get a negative Q. That just means that whatever direction you drew Q in, it's just going in the opposite direction.
Oh,
Yeah.
thank you.
Mm-hmm. Okay. So just like in the planar case, you know, thermal resistances really shine when you have a multi-layer system. Oops. Okay. And so this is a common situation when you have, multiple layers of different materials kind of wrapped around the same cylinder, okay? Okay, so let's say we have a situation like this. So this is quite common when you're doing some kind of a thermal insulation. So, maybe you have, this pipe, it's carrying some very hot liquid on the inside, okay? And then to protect the people on the outside, you have multiple layers of insulation kind of covering this entire thing, okay? Okay, so let's say that we have, this inner layer is just really, really hot. And so, I'll just kind of block it out like that, okay? This layer we'll say has a thermal conductivity Ka. This layer has a thermal conductivity Kb. And this third layer has a thermal conductivity K. So we have 3 layers kind of wrapped on top of each other, okay? And if we draw the radii here, okay, this is R1, R2, R3, R4, okay? Okay. Other thing I'm going to draw here is, let's say that we have convection on the outside. So convection still exists in cylindrical systems. Right. And so with convection, we have a coefficient of convection coefficient H. And we have the ambient temperature T infinity. Okay. Okay. Oh, one more thing that we need. We need the temperature of the inner surface. So let's say that the inner surface here, so right at R1, we know that temperature, we'll say that temperature is Ti. Okay. Okay, so for this example, it's fairly straightforward, but let's just write a question here. So let's compute, or let's come up with an expression. Okay. There's no numbers here just because this example is meant to be fairly quick. But let's come up with an expression that shows how much heat loss is coming from the inner part of the cylinder to the fluid. Okay. Okay. So from the problem here, you can see that it's asking for heat loss. So heat loss, I'm going to start to throw, different kind of terminology at you guys, but heat loss is just basically asking for Q, right? So heat loss or heat gain, that's the same thing as heat transfer rate, okay? And so since we're solving for Q, if we kind of scroll up here to our thermal resistance, right? The easiest way to do that in this situation is to use a thermal circuit, okay? The only difference here is that, our thermal circuit is going to involve 4 resistors, actually. So we have 3 conduction resistors and 1 convection resistance. Okay. Okay, so let's go ahead and draw the thermal circuit for this problem. Okay. And just like I noted, we're going to have 3 conduction layers. Right? Each of those 3 conduction layers corresponds to our 3 materials here, Ka, Kb, and Kc. And we're going to have 1 convection layer for the outermost one. Okay. So let's go and do that. So we have, so our leftmost node here is going to be Ti. Our outermost node here is going to be T infinity. And then in between those two nodes, we're going to draw our 4 resistors. So 1, 2, 3, 4. Okay. All right, so let's go from the inside out, right? So from the innermost layer bordering Ti, so going from Ti to the next layer here, we pass through material Ka. So we need the conduction resistance of that layer, okay? So this is going to be R conduction 1, okay? So let's go ahead and plug in our formula for conduction resistance. So we have Ln, okay? The outer radius of that layer is R2. The inner radius of that layer is R1. Okay, so we have ln of R2 over R1 divided by 2 pi times K of that layer, which is Ka, times the length. Okay. And we're going to assume that we know the length of this pipe here. Okay. Okay. So that's our first resistance, right? So going through material Ka. Once we reach radius R2, we're going to pass through another layer. So that's going to be layer Kb. So let's go ahead and write out the conduction resistance for that. Okay, so that's another conduction resistance. So our formula here is going to be the same, except we're just going to swap out the values here. So for layer B, we have ln of R3 divided by R2 divided by 2 pi Kb times L. Okay. So once again, utilizing the same formula here, but, with the different radii, because for layer B right here, the outer radius is R3, inner radius is R2, okay? Our third resistor here is also a conduction resistance, and so we have natural logarithm of R4 divided by R3 divided by 2 pi Kc times L. Okay. So that's pretty straightforward. So we have 3 conduction layers, 3 conduction resistances. You want to be careful in here because it gets a little bit repetitive sometimes when you're kind of applying the same formula. So just make sure, especially when you're plugging in numbers, make sure you plug in the correct values for the radius. You're plugging in the correct values for thermal conductivity for each layer, right? So just the way that heat transfer is, a lot of times we solve the problem first using symbols and then we plug the numbers in after. Just kind of be careful as you're kind of plugging numbers in, because it's easy to kind of miss something in the details. Okay. All right. Any questions on this so far? Yeah.
What is the L?
The L is the length of the cylinder going into the page. Yeah. So it's a bit hard to see because I always just draw the cross section, but the cylinder actually goes into the page like that direction. So the L kind of represents that length. Yeah. Okay. All right. So let's do the convection layer now. Finally. Okay. So I saved this one for last because it is a little bit interesting. Okay. So our formula for the convection resistance is actually the same as it was in conduction, right? So if you remember, our convection resistance was equal to 1 over H times A, right? Where this A right here represented the cross-sectional area across which the heat transfer was taking place. Okay. Okay. So I want to kind of bring this up again because in a planar situation, right? So back when we were in good old Cartesian coordinates, right? We had convection going across here, right? And we had heat transfer coming out here, right? This cross-sectional area, if you look a little bit closer, you can see this cross-sectional area was the area that was perpendicular to the direction of heat transfer. Okay. So basically, we looked at the direction of Q, and then we found the area that was perpendicular to that, and that's the area that we plugged into our convection resistance here. Okay. Now you have to be careful here with radial systems because you want to make sure that you plug in the correct area. So we're going to use the same formula here. So this last resistance here is just 1 over H times A. Okay. But now the question is, what do we plug in for the area for this expression here? Okay. So if we come back up to the diagram here, right? One thing you might say is that, like, okay, the convection heat transfer is occurring on the outermost layer right here, right? So we have this circle here, which has radius R4. And so you might say, okay, that area that we're going to plug in should be pi R4 squared, right? Because that's the area of a circle, right? But, if you look at that area is this one right here, right? So that's the area that we kind of see in the page. That's not the area that's perpendicular to the heat transfer, right? Because we know the heat transfer is going from inside out, right? So that area is not actually the area of the circle, right? The area that we actually want is actually the surface area of the cylinder on the outside, okay? So this area is actually surface area of cylinder. Okay. Specifically, it's the surface area of the cylinder that's bordering the fluid or that touches the convection fluid. Okay. In fact, actually, there's a little bit of a hint in our conduction resistances too, because we partially have that area here. Okay. So that area that we're plugging in there, the surface area, is 2 pi R4, which is the perimeter of the cylinder multiplied by the length of the cylinder. Okay. All right, so you want to be careful because when you're computing convection resistances, you always want to compute surface area, because that is the area at which the heat transfer is going past. Okay, because later on, we're going to go over convection resistance for a sphere, and then that's going to be kind of the same thing where we would use the surface area of the sphere as our area. Okay. All right, any questions on that? Why we choose that area there? Okay. All right. So now that we have our thermal circuit complete, let's go ahead and write out our expression for the heat loss. Okay. So Q loss here is going to be equal to, it's going to be a fairly long expression because we have 4 resistances, but we have Ti minus T infinity up top. Okay. And then on the bottom, we're going to sum up all of our resistances here. So we have natural logarithm of R2 divided by R1 divided by 2 pi Ka times L plus natural logarithm of R3 divided by R2 divided by 2 pi Kb times L plus natural logarithm of R4 divided by R3 divided by 2 pi Kc times L. It's even getting repetitive for me to just say all these natural logarithms. And then we have the convection resistance, so it's 1 over H times the surface area, which is 2 pi R4 L. Okay. And of course, if you have numbers for all these things, you have numbers for the temperatures, the radii, the thermal properties, the convection coefficient, then, you can plug in here and get a number for that. Okay. Okay. Question, yes.
Previously, when we were working in Cartesian, we were able to pull the A from it and
Yep.
get the heat flux.
Mhm.
Are we able to do something like that in cylindrical as well? Or not?
Not quite, because the area is kind of always kind of changing, right? Because the heat transfer is going radially outwards, kind of the surface area for that heat transfer is actually changing quite a bit. So in this case, you can pull out the L, so that is one thing you can pull out. So if you look at every term here has an L. So you can do a heat transfer per length, which doesn't quite have a name. The heat transfer per area is called heat flux, but in this case, we can do heat transfer per length. So that is one thing you can do, but because that cross section is changing, it's a little bit harder to compute the heat flux. Yeah,
Thank you.
yeah, good observation. Okay. All right. So that is thermal circuits in cylindrical systems. Now, before we move on to spherical systems, there is one thing that I do want to highlight here, which is actually quite fascinating. And actually, that question is kind of segues into that really nicely. So actually, let me take that situation from above and let me draw kind of a smaller version of it. So I'm going to draw a version that just has one conduction layer and convection, right? So we have one cylinder with one layer here, okay? And we have convection on the outside, okay? Okay, so we have an inner radius, outer radius, right? Convection, we'll assume we know everything about that. So we assume we know the convection coefficient and the ambient temperature. And we'll assume that we know the inner temperature of the inner cylinder, Ti. Okay. Okay. So this system right here has two resistances. Right. We have one conduction resistance, one convection resistance. I'm not going to draw the circuit just because it's very obvious. But I do want to write out the expression for both of the resistances. Okay. So we have conduction resistance is equal to natural logarithm of Rho divided by Ri divided by 2 pi K times L. And then convection resistance for a cylinder is 1 over H times 2 pi Rho times L. Okay. So similar situation as the last time is just, I just took off two of the layers here, okay? All right, so why are we looking at this? So why are we looking at a simplified version of the last example? So I want to highlight one particular variable here, which is the outer radius, okay? So you can see the outer radius actually appears in both expressions here. So it appears in the conduction resistance and the convection resistance. Okay. But the position or where that outer radius actually shows up in both equations is actually different, right? And so if you look at the conduction resistance, the outer radius appears in the numerator of that expression, right? Now, we're taking the natural logarithm of it, so that's going to, affect its value. But at the end of the day, it is in the numerator, right? And so, that kind of, makes you question of, what happens to this resistance as we increase that outer resistance or decrease that outer radius. I keep saying resistance, but I mean radius, right? So if we increase, okay, so let's say we increase the value of Rho, so we basically make the cylinder thicker, right? So we hold the inner radius constant, but we, let's say that we get a thicker cylinder, right? What is that going to do? That's going to increase the conduction resistance. Right? So that intuitively makes sense, right? And so, if you think about the situation from last time, if you have a very hot fluid on the inside, you want to insulate the outside so you don't burn yourself when you touch the pipe, right? The instinctive thing to do is just to make the insulation thicker, right? If you make the insulation thicker, it's going to cause more resistance to heat transfer, and it's going to overall reduce the amount of heat loss that comes out. Okay, so that makes sense. But if you look at the convection resistance, right, and if we consider the same phenomenon, so let's say if we increase RO, right? So we make the cylinder thicker, right? But if you look at the formula for the convection resistance, RO is actually in the denominator, right? So what does that mean, right? So if you make your denominator bigger, what that's going to do is that it's going to make your quantity smaller, right? And so the convection resistance actually has the opposite effect. So if we increase RO, this will cause the convection resistance to decrease. Now, that seems like kind of a paradoxical thing, right? But if you think about the way convection works, right? Convection is a surface effect. And so, convection basically tells you how much heat is being lost to a fluid that's being in contact with the surface, right? Now, radial systems are unique in that as you increase the radius of a radial system, right? So you take a cylinder, you increase its radius, you're also increasing the surface area. Right? And increasing the surface area means that there's just more places or more area for the cylinder to lose heat due to convection. Okay. So this connection between surface area and convection heat transfer is actually a very important, I would say, kind of design consideration when you're thinking of thermal systems. Okay. I'm going to jump ahead a little bit. So the next section that we're covering after spherical heat transfer is the concept of fins. So a fin is something you often design into a thermal system to increase the surface area to allow more heat to escape. Right. If you've ever looked inside a computer, or if you looked inside an engine, both are kind of the same. Both are kind of devices that kind of produce a lot of heat. You're going to see a lot of kind of spiky kind of geometry in that system, right? The purpose of those spikes they're not cosmetic. They're actually meant to increase the amount of surface area so that heat can actually escape from your engine or computer much more easily. Okay. So this idea of increasing surface area to encourage heat loss is something that's very prevalent. It's a core, I would say, core design philosophy for thermal engineering in general. Okay, but if you look at this kind of very simply, just for a cylindrical system, this makes a lot of sense. And so when you increase the radius, you increase surface area, you just make it easier for convection heat transfer to occur. And so it makes sense that the resistance or convection resistance is going to decrease as you increase the radius. All right. Any questions on, does that kind of make sense about kind of why we have this kind of dual thing going on? Good. All right, so in other words, you know, we have kind of competing effects. Right? So on the one hand, if you increase the radius, you're making it harder for conduction heat transfer to occur, but you're also making it easier for convection heat transfer to occur. And competing effects is one of the most, I would say, fascinating things that can occur in kind of in almost anything. So science, economics, finances, you know, when you have two things that are competing, you know, it means that, you know, whenever you do one thing, you're kind of trading off other thing. Okay. One thing that this always implies, though, is that there's always some kind of sweet spot. So whenever you have two competing effects in you know that are, you know, shown mathematically, there should be some kind of sweet spot where both effects are kind of minimized, or there's kind of a nice balance between the two. Okay. And so this idea gives rise to something called the critical thickness of a cylindrical system. Okay. So what is this critical thickness? So to compute the critical thickness, or even to just kind of understand what it is, question, yes. Oh, question, sorry, right in front of me.
So you're saying when you increase the outer radius, then conduction resistance increases.
Yes,
But conduction heat transfer decreases.
yes,
And then vice versa for convection.
exactly.
Okay.
Yeah.
Okay. Just making
Because
sure.
you're right, because the kind of the fundamental formula that we have is Q is equal to delta T divided by resistance, right?
Yeah, okay.
So if resistance goes up, then heat transfer goes down. Yeah. Thank you. Sometimes I get so into it. Just say something in those situations. Okay. All right. So first, you know, let's write out an equation for the total resistance. So total resistance here is just going to be the sum of our conduction resistance and the convection resistance. Okay? So we have ln of Rho divided by Ri divided by 2 pi K times L plus the convection resistance, which is 1 over H times 2 pi Rho L. Okay. All right, so that's a total amount of thermal resistance that's going to be, you know, that's going to be there in our system. Okay. Now, the variable in question here, of course, is the outer radius. Okay. So to find a sweet spot, or where this resistance here is going to kind of balance, or these resistances are going to balance, let's take the derivative of this total resistance with respect to that outer radius. Yeah.
So so thermal conductivity, K, does that doesn't play in convection, like the convection resistance? Why?
Yeah, so the thermal conductivity is just a material constant of the solid cylinder itself, whereas convection is the amount of heat that's going to the fluid that's on the outside. So so the thermal conductivity is only going to play a role in conduction, but not in convection.
Solid.
Exactly. Yeah. So the conduction resistance basically represents the heat transfer through that solid part of the cylinder, whereas the convection is the heat transfer to the fluid part itself.
So I know we'll probably get to this when we're talking more about convection. But do different gases do interact with heat differently?
Yep. Yep. So actually every fluid, every liquid and every gas has its own thermal conductivity too. So it's not just something that's unique to solids. It's just usually for liquids and gases, they're usually in motion. And so the convection coefficient H actually factors in that K for that fluid also into account too. So that H is the combination of both kind of the thermal conductivity of that gas or liquid, as well as its motion as well.
The motion of the fluid.
Exactly. Yeah.
So like pressure gradient across the surface?
Yep. As well as if it's laminar or turbulent, that's going to play an effect too. Okay. So if we take this total resistance here and we take its derivative and set it equal to 0, that's going to tell us, whether we're that's going to show us where we have a maximum or a minimum of this total resistance. Okay, so we're going to take the derivative of the above expression and set it equal to 0. Okay. All right, so we're going to take the derivative of the first term there. So the derivative of that first term is 1 over 2 pi RO times K times L. Okay. So we're basically taking the derivative of natural logarithm of RO. So the derivative of that is just 1 over RO. Okay. And then the derivative of the next one is we have minus 1 over H times 2 pi RO squared times L. Okay. Because we're just taking the derivative of RO to the minus 1 power. Okay. So that minus sign comes out in front, and then RO becomes RO squared. Okay. Okay, so now we can take this expression and we can solve it for RO, right? Because we have an expression here that's set equal to 0, right? Luckily, we have a lot of terms here that are going to cancel out. So we have 2 pi on both terms, and so I'm just going to cancel those out. We have L on both terms. That's going to cancel out as well. Okay. Question, yes.
Is the Ri included in this first derivative?
So in this case, Ri is just a constant. And so remember, ln of Ro divided by Ri, we kind of split that up into 2 natural logarithms. So ln of Ro minus ln of Ri. And so ln of Ri is just a constant. So we take the derivative, it just goes away. Yeah. Okay. And so we have all those terms cancel out. And so we have 0 is equal to 1 over Ro times K minus 1 over H Ro squared. Okay. Okay. Question. Yes.
Cancel one of the ROs?
You could, yes. And in fact, we will, but then yeah. Yeah, so let's cancel one of the ROs. And so we solve this for RO, right? Let's see. So let's put the 1 over H RO on this side. This is equal to 1 over K. Let's just invert this whole thing. So we have H RO is equal to K. Okay. So I'm just doing some fast algebra here. And then RO we get is equal to K over H. Okay. No, so it actually has units of length here because it's a radius. Right, so this value of RO, this right here represents the critical thickness of a cylindrical system.
Is K and H, are those material properties?
The K is, so the K is a material property of the solid, of the cylinder, but the H is a property of the fluid. So it depends on the thermal conductivity of the fluid itself, but it also depends on the motion too. Yeah. So H is something that we're going to solve for in the second unit on convection. Yeah, so H can vary actually quite a bit. So whether you have like a still fluid or like a fast moving fluid, it's going to change.
But when it's like steel or anything like that, the K will always be consistent.
Exactly.
Despite the size.
Exactly. Yeah. So the K is kind of like,
So H is what determines.
you could say that. Yeah. So the H is usually something you have a much bigger influence on because you can either put a fan there, or you can change kind of the properties of the fluid a lot more easily than the solid itself. Because the solid usually has a fixed thermal conductivity. Yeah. Mhm. Okay. So we've solved for where this basically the conduction and convection resistance are balanced. We basically found where the total thermal resistance reached a maxima or a minima. Okay. You can take one more derivative. Right. So if we take one more derivative of the total resistance, we can determine if this is either a max or a min. This is optimization all over again. So it turns out, so I'll spare you the math, just that I do want to get to spherical stuff. It turns out this critical thickness here is a minimum of the thermal resistance. Okay. And so if you plot out, actually, so if I kind of show you a plot here. And so if you plot out the total thermal resistance of a cylindrical system as a function of the outer radius, right? It actually kind of shows kind of almost like a parabolic type of behavior. And so there's a certain regime where as you increase the radius, the total resistance actually goes down, right? Which is really fascinating because, like I said, intuitively, what most people think when you have a system, you want to increase the resistance, you make it thicker. But sometimes you could actually be making the situation worse just by increasing the surface area, right? Eventually, this curve here is going to bottom out at its minimum. Okay. So this minimum right here, this is the critical thickness. And then it's going to pick back up again. So this concept of a critical thickness of, by adding insulation, sometimes you make it actually easier for heat transfer to occur. This is something that's unique to radial systems. And it's a big reason why this is kind of its own unit in the heat transfer kind of, space here. Because usually, for most classes, like fluid mechanics, solid mechanics, usually we don't pay too much attention to cylindrical coordinates or spherical coordinates. Here it actually makes a big difference because, a lot of times you'll be designing systems that are cylindrical or they're spherical, right? And you need to be aware of this phenomenon of critical thickness. So you don't accidentally make the situation worse by adding more insulation. All right. Yes.
Does that end up being like a pretty smooth curve, or is it kind of like big jumps?
It's pretty smooth. Yeah, it's smoother than what I drew it. Yeah. You basically have a competition of 1 over R versus ln of R. Yeah. So eventually the 1 over R will kind of die down and then the curve will look like natural logarithm.
Since I'm about checking this to make sure you're not making the situation worse.
Yeah, because if you're in this regime right here, right? So let's say that you want to insulate a system better, right? And you're asking yourself, should I add more insulation to make it, to make it more insulated? If you actually add more insulation in this regime, you're actually reducing the thermal resistance. And so you're making it so that there's more heat loss that's occurring if you're in that regime. And so if you're going to add thermal resistance, you want to make sure you add enough so that you're kind of in this regime over here. Yep.
So once you get past that threshold, it's just gonna increase linearly.
Exactly.
It is linear though.
It's natural logarithm, which looks linear at higher values. So yeah. Okay. All right. So that is the concept of critical thickness. Now there is the same concept of critical thickness for a sphere as well. So you can definitely go through that exercise. We won't be doing that in the lecture, but I think it's a good exercise to go through for a sphere, to see what the critical thickness for a spherical system is. Okay. All right. Speaking of the sphere, let's go ahead and move on to those. So let's look at the heat equation in spherical coordinates. Okay. So just like we did with the cylinder, and kind of just like we did in the planar systems, I'm going to write out the full heat equation in spherical coordinates, but just be aware that a lot of these terms are going to cancel from our assumptions. Okay, so the full heat equation, we have 1 over r squared partial r of k r squared partial t partial r plus 1 over r squared sine squared theta partial phi. Okay. Now the thing to remember that in spherical coordinates, we have 2 angular coordinates now. And so we have theta and phi. And I'll draw you the difference right after this. Okay. This is multiplied by k partial t partial phi. And plus 1 over r squared sine theta partial theta k sine theta partial t partial theta. Okay. That's the scary part. Plus q dot is equal to rho cp partial t partial t.
The second term is sine squared and the third term is not sine squared.
Exactly. Yeah. Mhm. Okay. Question? Yes.
What's the subscript on this?
CP. Oh, thank you. I don't know why I wrote a 2 there. I'm thinking ahead to my next class, which is 308. We're doing a second order ODEs right now. Okay. So, of course, this equation here assumes we're having spherical coordinates. And so the 3 spherical coordinates here are r, phi, and theta. Okay. R here is known as the radial coordinate, so that's the same, or you interpret that kind of the same way as the cylinder. So the radial coordinate is one that points from the center out towards the outside. Okay. Except now we have a sphere, so it's pointing from the center of the sphere to the outside. Okay. Phi here is known as the azimuthal angle. And I don't even know how to spell it. Azimuthal angle. Okay. And theta here is the polar angle. Okay. And so if you draw it out, you draw a sphere here, something like this. Okay. The spherical coordinates are going to assume that you start from the inside of the sphere. Okay. So just like before, the radial coordinate goes from the inside to the outside, okay? The polar coordinate is this angle right here, okay? Right, so it's an angle that's kind of in this case in the plane. Okay? And the azimuthal angle, it's a little bit hard to tell, but you know, it's an angle that's kind of in the plane that's perpendicular to that. Okay? So if you kind of look at this, the polar angle is in a plane that's parallel to the page. The azimuthal angle is going into and out of the page, okay? But they're all kind of going circular, okay?
The XY plane.
Yeah, you can say it like that. Yeah.
That one only goes from 0 to 180.
Exactly, yeah. Yeah, so the azimuthal angle only goes from 0 to 180. The polar angle goes from 0 to 360. Okay. Now, of course, you know, this, you know, we're never going to solve this entire full equation here. And so we're going to be applying a lot of assumptions. Okay. Basically, any derivative with respect to an angle here, we're going to assume it's 0. Okay. So the first assumption that we always make is we're going to assume steady state. Right? So steady state we know. So steady state means that any derivative with respect to time is going to go to 0. Okay, partial t is equal to 0. Second assumption that we're always going to make is that we're going to assume that the situation is only 1D and it's only in the radial direction. So any derivative with respect to theta, any derivative with respect to phi, it's going to be equal to 0. Okay. So that takes care of most of those terms. And the last one that we'll make most of the time is we're going to assume that there's no thermal production. Okay. No thermal production means that the Q dot term is going to be equal to 0. Okay, so we apply these assumptions to our heat equation. It's going to cancel out basically every single term except for one. Okay, so let me come up here. First term here, that's the only term we're going to keep because that has derivatives with respect to R. Okay, second term, we have a derivatives with respect to an angle here. So that's the derivative with respect to the azimuthal angle. And so that's going to be 0. Third term, we have derivatives with respect to the polar angle. And so this one also we're going to assume it's going to be 0. Okay. Next term, we have thermal production. So thermal production, we're just going to be setting it equal to 0 as well. And then finally, the unsteady term. And so the unsteady term has a derivative with respect to t. And so that's going to be equal to 0. Okay. So in reality, you know, you would solve this if you had kind of a generic kind of a 3D spherical system. You could solve all of these terms at once. Probably you're going to use some kind of computer software to do it. But you know, for our purposes, just so that we can solve them by hand, we're going to assume most of these are 0. Okay. Okay. So all that we're left with after all of those cancellations is just this one term. So let me go ahead and write it out. Okay. So after applying all those assumptions, all that we're left with is 1 over r squared ddr. And since we only have one independent variable left, I'm going to change that derivative to a regular derivative. K R squared dt dr. All that's equal to 0. Okay. All right, and so that's going to be the starting point for our first example that we're going to do today. Okay. All right, any questions on that? How we got to that point? Okay. All right, so last thing we're going to do today, let's solve this equation for kind of a very classical case. So just like we did for the planar system, just like we did for the cylindrical system, let's solve this heat equation for a situation where we have two prescribed temperatures. Okay, so we're going to have a hollow sphere. I know it looks like a cylinder, but assume that there's a curve there. Okay, so this is a sphere. We have an inner radius and an outer radius, RO. Okay. Inner radius has a temperature Ti. Outer radius is temperature TO. Right, so that's going to give us the following boundary conditions. Okay. We have T at Ri is equal to Ti, and then T at Ro is equal to TO. Okay. All right, so classical situation, we have two prescribed temperatures, hollow sphere, inner and outer radius. So just like we've done, quite a few times already, let's solve the heat equation. Okay. So we're going to solve the heat equation for the temperature distribution inside the sphere. Okay. And all of the assumptions that we're going to be assuming is the same as it is above. Okay. So just for this example, I'm gonna start from this heat equation that we have here. But just know that where we got this was from the full heat equation just after canceling all those terms. Okay. All right. Any questions on just on the setup for the problem? Okay, so let's go ahead and solve. So let's start from, we're starting from the 1D heat equation. So starting from the 1D heat equation in spherical coordinates, we have 1 over r squared ddr of k r squared dt dr is equal to 0. Okay. So we're going to integrate this twice, but all the addition of all of these r terms will make it a little bit more complicated than usual. Okay. This looks very similar to our cylindrical heat equation here, except instead of r, we have r squared. Okay, in both of those places. Okay. All right, so first thing I'm going to do, just so that we can take that first integral with respect to r, let's multiply both sides by r squared. Okay. Another thing I'm going to do in this first step here is I'm going to factor out this k. Okay. So that thermal conductivity is just a constant, and so we can pull it out of that derivative, and so we can just kind of multiply both sides by that. So I'm gonna take this and we're gonna multiply by r squared over k. Okay. So that's gonna cancel out this r squared here. So I put the 2 in the wrong place. Okay. So that r squared is gonna cancel out with that r squared. That k is gonna cancel out with that k because we pulled it out of the derivative. Okay. And then what we're left with is ddr of r squared dt dr is equal to 0. Okay. Okay, so now that we have it in this form, we can just simply integrate, right? The derivative is exposed right there. So if we just take an integral just like that, it's going to cancel out with that derivative. Okay. Okay. And so on the left-hand side, we just have a simple cancellation of the integral and the derivative. And so we have r squared dt dr is equal to integral of 0. So integral of 0 is just 0. But since we're doing an indefinite integral here, then we have to add our arbitrary constant, C1. Right. So before we can perform the next integral here, let's divide both sides by r squared. Okay. So that's going to get rid of the r squared on that side. On the right-hand side, we're going to have C1 over r squared. So we have dt dr is equal to C1 over r squared. Okay. Okay. Let's go ahead and take this integral one more time. We take the integral one more time, we get t of r is equal to so integral of C1 over r squared, that's going to be a minus C1 over r. Okay. But since the C1 is still arbitrary at this point, we haven't assigned its value. I'm just going to take that -1 and just kind of lump it together. Okay. So we end up with C1 over r plus C2. Okay. And so this right here is our general solution. So now at this point, we need to apply boundary conditions to solve for C1 and C2. All right, any questions on this? Okay. All right, so let's go ahead and apply our boundary conditions. Okay. And so first we have T and R is equal to R1 or Ri, excuse me. That's equal to Ti. Okay. So if we plug that in, we get C1 divided by Ri plus C2. Okay. Our next boundary condition, T when R is equal to Ro, this is equal to To. Okay. That's C1 over Ro plus C2. Okay. Okay, so we have two equations here to solve for our two unknowns, C1 and C2. Okay. So let's go ahead and solve this system. So what I'm going to do, kind of my usual trick here, just because we have a positive C2 on both terms. So let's subtract these two equations. And so subtracting these two equations, we have Ti minus To is equal to C1 over Ri minus C1 over Ro. Okay. The two C2s are going to cancel out. And so we can take this expression and solve it for C1 very easily. So on the right-hand side there, we factor out C1. So we have C1 multiplied by quantity 1 over Ri minus 1 over Ro is equal to Ti minus To. And so we just simply divide both sides by the quantity in the brackets. That's going to give us our expression for C1. Okay. So C1 is equal to Ti minus To divided by 1 over Ri minus 1 over Ro. Yeah. Okay. So that is our expression for C1. And so we can now take this expression for C1 and plug it back into either of these equations to solve for C2. Okay. So I'm just going to take this and plug it back into equation 1. Okay. Right. So we're going to plug back in, solve for C2. Okay. And so we plug this back into equation 1. What we get is 1 over Ri multiplied by C1, which is Ti minus To, divided by 1 over Ri minus 1 over Ro, plus C2 is equal to Ti. All right, and so we're just going to simply subtract that first term there, that kind of big term right there to solve for C2. Okay. And so we get C2 is equal to Ti minus 1 over Ri times quantity Ti minus To divided by 1 over Ri minus 1 over Ro. Okay. All right. And so we plug this back in, and then we're going to get our expression for the temperature distribution. Okay, so we're going to plug C1 and C2 back into our general solution. Okay. And so T of R then is equal to 1 over R multiplied by Ti minus To divided by 1 over Ri minus 1 over Ro plus Ti minus 1 over Ri Ti minus To divided by 1 over Ri minus 1 over Ro. All right. So this right here is our final solution here. If you look into the textbook, if you look at the answer to this example, because this example is very classic, they're going to have a different form of the solution. So that form and this form are one and the same. Just the other form has, they've kind of massaged this algebraically a little bit. So they've rearranged some terms, they've kind of combined some like terms, just to make it a little bit more compact. But this one, is perfectly valid, and it's the one that you get kind of directly from solving for C1 and C2. Okay. Okay. Any questions on this? Okay. Last thing I want to do before we leave is, just like we did in the cylindrical system, just like we did in the planar system, let's take this expression here and use it to derive a formula for the thermal resistance for a sphere. Right, because eventually what we're going to be doing with spheres, just like we did with cylinders and just like we did with planar systems, is we're going to be solving thermal circuit type problems. And so in order to do that, we need to get the conduction resistance for a sphere. Okay. So just like we did before, let's go ahead and plug this expression into Fourier's law. So remember, Fourier's law is equal to, or Fourier's law states that the heat transfer in a thermal situation is equal to minus K times the area dTdr. Okay. Now for dTdr, we're going to plug in the expression that we have above here. So we're just going to take the derivative of this expression with respect to r. Okay. You're going to see that a lot of the terms are going to cancel out. So it's actually going to be quite simple. Okay. The other thing that we need to plug in here is we need to plug in the area. Okay. And so just like we saw with the cylinder, this area that we're going to plug in is the surface area of a sphere. It's going to be the surface area of a sphere with radius r. Okay. So this formula might be a little bit less known just because, just typically we don't work with spherical systems all that much. So I'm just going to go ahead and give it to you. So the surface area of a sphere is 4 pi radius squared. Okay. Okay. So let's go ahead and plug everything in here. Okay. Okay. So if we plug that in, we get Q is equal to minus K times 4 pi r squared. Okay. We're going to take the derivative of our temperature distribution with respect to r. Okay. So if we come back up to this temperature distribution, we're going to take the derivative with respect to r, which sounds scary, but if you see, the only term here that has the radius is actually this first term. So this entire term here, when we take the derivative, is just going to cancel out. Okay. Right? Because all of those terms there are just constants. And then we take the derivative of that first term there, we get minus 1 over r squared multiplied by C1, which was Ti minus To divided by 1 over Ri divided by 1 over Ri. Okay. All right. And so a bunch of this is going to cancel, right? So we have r squared is going to cancel with r squared. The negative is going to cancel out with that negative. Okay. And so just quickly, just because we're almost out of time, I'm just going to rearrange this. So we have Q is equal to Ti minus To divided by 1. Let me put this in square brackets because it's a little bit messy. 1 over Ri minus 1 over Ro divided by 4 pi K. Okay. Right, so that 4 pi K came from the numerator on the previous one, but I just put it in the denominator here just so it can all be together, because this quantity right here, okay, this is the conduction resistance of a sphere. All right, so when we come back on Tuesday, we're going to start, well, I have one more example with the heat equation for a sphere for you. This one has thermal production. So that'll actually be useful for your homework for the next one that I'm going to post. And then we'll do a very quick example using thermal circuits for a sphere. Okay. All right, so thank you guys for coming today. Hope you guys have a good, a weekend, rest of your day, and I will see you guys on Tuesday. Sure.
So I was getting my negatives, my signs mixed up on problem 2, and I was talking to Blake, and he said that right here at the K, you don't include the negatives.
Yeah, so when you're in this form right here, infinity minus L, the negative from here actually kind of factors in.
It goes into the new spot.
Yeah, because in traditionally the T, the surface temperature. But if you take that negative and put it over here.
Okay.
So if you're using this one, then it's the negative out there.
Oh, okay, okay.
Yeah, so for this one, you know, we have a different. So eventually we want to have all, so right now we. So my. So we kind of really kind of take it. Zero. You know, usually when I'm solving one program, I want to take it. But if there's kind of like things that are in the way.
That's all of that.
Exactly.
You're done. Wait, does that mean?
I don't think you have to do all They're not that hard.
Yeah.
I was wondering.
Yeah, so you find out. That's actually a good one. Double prime. The P flux is Q of K, so it's basically heat transfer rate per unit. And then Q dot is something special, that's thermal production of the production of thermal. Yeah, thermal production usually it's not going to be there, but it's usually kind of by.
Okay,
Yeah,
okay.
for sure.
Thank you.
Yep.
I always thought.
Questions about that?
Sure.
I know you have office hours at 2:30.
Yes.
Better just to go over there.
Sure, yeah, if it's quick, I can answer right now, but if not, then.
It's a couple of.
Okay, let's talk in office hours. Yeah, let me go back to my office, let me get settled, and I'll open the door.
That's fine.
Okay.
Where
Is force?
What's over here?
It's just right down the hall back. Yeah, walk past the bathroom, then turn right.
Okay.
Yeah.
You're doing force